This video is for the notes on slope fields and differential equations. This is on page something in your packet, number 1. We're going to draw a slope field by hand for each differential equation and find the general solution for the differential equation. Use the given ordered pair to find the particular solution that passes through the point. That's a lot of words. So let's go on and start. In class, what I did is I made you guys a xy, dy, dx table just to plug in some values here. So let's go ahead and do that, xy, dy, dx. We can plug in any number that we want, but we do have to plug in every single lattice point, every single point that you see here we have to plug in. So if we plug in 0 when x equals 0, there is no y value. This derivative is not dependent on y, so we can actually cross this off. When we plug in 0, we get 0, which means this is great news for us because anytime x equals 0, no matter what the y value is, we're going to get a slope of 0, and a slope of 0 is a horizontal line, which is why I'm drawing these horizontal tangents here. When x equals 1, so when x equals 1, I get a -4 slope because -4 times 1 is -4. Then a -4 slope is going to be a steep slope. And the way I look at it is I kind of try to go down 4 and over 1, and I'm aiming for this point when I draw the line. Something to that effect. And that's for all x equals -1s. And again, it's to the best of your ability. For x equals 2, we have -8. So for x equals 2, you have -8. That's an 8, and it's negative. And again, it's even steeper slopes. Not vertical, but much steeper than the last one. And same with x equals 3. These are really steep lines. Steep, steep, steep. And the nice thing about this is that we have some symmetry here, because when x equals -1, we just get the opposite slope. We get the change in sign. So now we're going to have a +4, and a +4, and a +4, and a +4, and a +4. When x equals -2, we're going to get a +8, and a +8, and a +8, and a +8, and a +8. When x equals 3, we're going to get a +12, 12, 12. Okay, so now let's get the general solution. The general solution means I need to solve for y. So that's I'm going to take dy dx equals -4x. I'm going to separate the variables. That's always your first step. So dy equals -4x dx. One reminder here, never get dy and dx on the bottom. If you get dy dx on the bottom, it's a huge error for you. Dy dx should always be on the top when you're integrating. Let's go. Sorry, integrate. Oh, geez, I'm tired. And I get the integral of y, dy, which is y. So I get y equals antiderivative of -4x is -2x squared because it's -4x squared over 2. And then it's plus c. This is your general solution. It's already solved for c. I'm going to make a note here that the general solution is always in terms of y. So general solution is always in terms of y, which means in short, solve for y. All right, here, particular solution solves for c. And is written in terms of y. Okay, so that's our first part for the general solution. Let's go and get the particular solution. So what we can do is we can plug in our point, and our point was 1, 1. That was given right here, so let's go and plug in a 1 equals 1 for y and 1 for x, -2, 1 squared plus c. And if my math is correct, and I think it is because it's just a great math day, c equals 3. So now I'm going to take this green box, and I'm going to go and plug in c here. I'm going to make this purple now. Y equals -2x squared plus 3. And this is my particular solution for the differential equation. Also important to note, I could sketch my particular solution. So if I sketch my particular solution with a negative of 1, 1, so here's 1 and 1. If I follow these lines here, and it goes up, but then it goes down. It's kind of dropping fast, and that would be the graph of y equals -2x squared plus 3. That's a sketch of it. Notice my graph doesn't exactly go through the y-intercept of 3, so maybe I would have had to do that a little bit better. So let me just try to do that a little bit better here of sketching this graph, and then I'm going to go and keep going. So let's just go up more. And maybe that's more of what it would look like. Okay, let's go on to the next problem, number 2. Okay, so we got dy dx equals negative 1 over 2y. I'm going to pause the video and allow you to try sketch the slope field first, and then I'll walk you through the general solution, particular solution afterwards. But please sketch the slope field now. So hopefully this is what your graph looks like, or your slope field looks like. Now let's go and get the general solution plus c. I hope there were no questions actually on the slope field. I basically plugged in a y value because the differential equation only takes y's, and I plotted what the slope was. The blue ones were 1/4 and negative 1/4. The green ones were 1/2, and the red ones were negative 1/2. So again, hopefully you will see that. Let's go ahead and go with dy dx equals negative 1 over 2y. So first I need to separate the variables, which means I'm going to multiply by 2y. I could just multiply by y actually if I wanted to, so I'll just multiply by y on both sides, and I'll multiply by dx on both sides, and I end up getting, actually I'm not going to write that out because that's technically not correct, but I won't talk about that. Just know that you have to get your variables on one side, same variables on the same sides. So y dy is equal to negative 1/2 dx. And again, there's a lot of ways that you could have gone about this. If you had the 2y, dy equals negative x dx, that's fine as well. Make sure you integrate both sides. So we get, and you can't integrate an equal sign, so my apologies there. So you get y squared over 2 is equal to negative 1/2 x plus c. We could get rid of those 2's by multiplying everything by 2, and you get y squared equals negative x plus c. We didn't multiply by 2c because c again just represents an entire number that we don't know. And to solve for y here, we get y is equal to the square root, plus or minus though, square root of negative x plus c, or c minus x, same thing. Negative x plus c, or c minus x. And now that is our answer for the general solution. So general solution is this one. Let's go and do a particular solution. It doesn't matter which equation you want to use for the particular solution, in the sense that if you choose either one of these two, so either this one or that one would be fine to be able to plug in x and y to get c. But what I'm going to do right now is I'm going to plug in negative 2 and 1 to solve for c, where x is negative 2. So I have negative 2, I'm choosing the first equation, plus c equals 1 squared. That's going to be 1 is equal to 2 plus c, which means c is equal to negative 1. So now I'm going to go ahead and rewrite my equation with y is equal to, and I'm just checking my work here for a second, I want to check something. That's right, which means y is going to be equal to plus and minus the square root of negative 1 minus x. Now what I want to do here is I want to think and make sure which one do I want. Do I want a plus or do I want a minus here? And there's a pretty straightforward way to tell. Let me just highlight this here. So do I want a plus or a minus? And the way I'm going to know is dependent on that sign. Because when I plug in negative 2 in for negative x, when I plug in negative 2 for negative x, I get negative 1 plus 2, and the square root of that is going to be a 1, and I do not want my answer to be a negative 1. Like if I put a negative here, I would get a negative 1, but I actually want a positive 1 out, because the 1 is the y value in my solution. In short, whatever the y value is, whatever sign the y value is, go with that sign for the function. So my final answer here is going to be y is equal to the square root of negative 1 minus x. That's the particular solution. If we were to sketch the solution curve, and it doesn't say that we need to, but if we were to sketch the solution curve at negative 2, 1, so here is negative 2 and 1, so here's my initial condition. And it looks like the graph is going to go like this, and I'll put this in a different color here. Looks like the graph is going to start here and then kind of curve down to be a vertical tangent, and maybe it would end up right here, I don't know, and then it grows off in that direction. That's what the solution curve would look like based on the slope field. The reason I moved it over to the 1 is because I had the knowledge of the equation. And the equation said that I had to have a, where am I here? The equation said that I had to have a 1 in there as the x-intercept. Rather, a -1 as the x-intercept. Okay, number 3. Actually, let's do this reflection. What pattern do you know is happening in the coordinate plane for number 1, and what about number 2? What part of the differential equation is creating that pattern? So what pattern do you know is happening in the coordinate plane for number 1? What pattern do you notice in the plane for number 1? Well, they're symmetric about the y-axis, and in number 2, we're symmetric about the x-axis. So, number 1 is symmetric about the y-axis, which means that when we have a number over x, we'll have symmetry about the y. And then number 2 is symmetric about the x-axis, and similar reasoning. Divided by y, and symmetry will be about the x. Okay. That's the pattern. And that's the part of the differential equation. We have that one x value that allows us to, and actually I don't think this is divided by x, but it's the same idea. We just have a number with an x. I'll change this slightly just to make it more ideal. When we just have one x and when we just have one y in the differential equation, then they'll be symmetric about those different axes. On to number 3, dy dx is equal to 3x squared, so we could use some symmetry here to kind of sketch these a little bit quicker. Please pause the video and try to sketch those on your own, and when you're ready, please unpause the video. When x equals 1, we'll have a slope of 3, which means we would go like this, kind of aim for a slope of 3. When x equals 2, we're going to have a really steep slope of 12. And then here for 3, oh my gosh, that's going to be a slope of 27, which is going to basically be vertical. All right, and now for x equals -1, looks like we're going to have a slope of 3 again. So actually, this looks like it's going to be pretty nice for us because that square is going to be the same thing on both sides. All right. This is kind of a weird one. Now, we would get a much better picture if we had more intervals here, but again, this is what we're given. That's our slope field. Let's do a general solution. So let's separate the variables. So dy dx is equal to 3x squared, which means that, actually I can just change this here to get the dx on the other side, and that's going to be 3x squared dx. Just get rid of all this. Okay, now let's integrate both sides because the variables are separated, and you're going to get y on the left side equals x cubed plus c. Okay, that's my general solution. The particular solution through 0, 1. Okay, so 0, 1, I'm going to have to use my general solution and plug in y equals 1 and x equals 0, and I get c equals 1. So that means my particular solution here is going to be y equals x cubed plus 1. Okay, and if I was to graph this, if they asked me to graph the particular solution, well, let's go to 0, 1, because that's where the initial condition is, and I'll just make a note of that. That's called an initial condition. It's the one point that they give us that is on the original function, and that allows us to sketch using the slope field the particular solution. Okay, so now let's just sketch and see what's going on here. I'm sorry. So at 0, 1, we have a horizontal tangent, then it looks like it just curves up really, really fast. And same here. It looks like it curves really, really fast and goes down really fast. And this equation is y equals x cubed plus 1, and that does look like y equals x cubed plus 1. Let's go to number 4. Yeah, number 4 is dy dx equals sine x, and this is the last one here. Count on the x-axis by multiples of 2. Okay, so we have pi over 2's here. So sine of pi over 2, I'll do this one with you. Sine of pi over 2 is 1, and I'll skip the table this time. So a slope of 1 looks something like this. Now we're going to have pi, because again we had multiples of pi over 2. 3 pi over 2. So sine of pi is 0, so let's go and do 0 slopes for pi. So sine of pi is 0, so that means we have 0 slope. And if you're not sure why, again, I just did sine of pi here to get 0. Then let's do sine of 3 pi over 2, and 3 pi over 2 is negative 1. So we have negative slopes here of negative 1, drawn to the best of our ability. I didn't finish up these, so I'll finish these up. Sine of 0 is 0, so we'll have a blue one again, and it looks like we're going to have a oscillating function here. It looks like it's going to be a trigonometric one, sinusoidal, if you will. On the other side, we have negative pi over 2. Negative pi over 2, we have negative pi, and we have negative 3 pi over 2. And if you're struggling with that unit circle, negative pi over 2 is right here. So that means we're going to be back to our negative 1 slope again. 1 slope, negative 1 slope, negative 1 slope. All right, and then negative pi is going to be fully around, so that's going to be where y equals 0, so 0 slope here. And then lastly, we have this one, slope of 1 for sine of negative 3 pi over 2. And that's kind of what we want. We want something oscillating here. Let's go and do a separate and integrate. So dy is equal to sine of x dx. And what we're going to do is we're going to integrate both sides. Antiderivative of dy is just y equals antiderivative of sine of x is going to be equal to negative cosine x plus c. So equals negative cosine of x plus c. And that is my general solution because it's solved for y and it still has a c. Okay, to do the particular solution through pi 2. Well, what we'll do here is we're going to go ahead and do, let me get rid of this. We're going to go and do y is equal to, I'm sorry here, that's not correct. We're going to go ahead and do, plug in 2 and pi for y and x. So 2 is equal to negative cosine of pi plus c. I think cosine of pi is negative 1, so this cancels out with the negative there, and we get 1c, 1 plus c, which means c equals 1. So my final answer here is going to be y is equal to negative cosine x plus 1. And to finish it up, the point pi comma 2 is right there. And if I was to sketch this, it would look something like this. Okay, and now it looks like it's curving. I think it curves a little bit before then, but okay, let's just assume that it's this. Maybe not. I think it actually goes down there. And then it's going to go back up again, and then it's going to curve again, and then it's going to go back down, and then this would be here. Now, it didn't ask us to do this, but again, I just want us to get used to sketching a solution curve through a slope field. And that's all for this video, guys. Thanks for watching, and I hope this helped.